Okay. Well, what I want to do tonight, as Barb kind of alluded to, is talk a little bit about some of the impacts that we're seeing currently from climate change, some of the projections, and talk a little bit about solutions, and primarily from the aspect of DCNR. So as it relates to state parks and state forests. So what I like to do is kind of start with just a little basic climate science, just make sure everybody's kind of on the same page. And the first thing we always want to talk about is the greenhouse effect. And the greenhouse effect is a naturally occurring phenomenon. Without it, we would not be able to live on this planet. And basically, the greenhouse effect just describes the fact that almost all the energy that our planet has or receives comes from the sun in the form of light. And when that light strikes the surface of the Earth, some of it bounces back into space as light, but a big chunk of it is converted to heat. Now, if we didn't have an atmosphere, all that heat would radiate back out into space and we wouldn't be able to live here. We'd be like Mars. But fortunately, we do have an atmosphere, and that atmosphere contains naturally occurring greenhouse gases, things like carbon dioxide and nitrous oxide and methane and a bunch of others. So if you think of our atmosphere as a blanket, an insulating blanket around the planet, those greenhouse gases are the fibers in the blanket. As you increase the number of fibers, in other words, as you increase greenhouse gases, you increase the thickness of the blanket and it holds in more heat. So that's kind of what's happening right now. Now, this graphic shows you that. Unfortunately, it shows the atmosphere as being kind of really thick, when in reality, it's actually very thin, fragile. So what we're going to do is just talk a little bit about one of the greenhouse gases tonight, and that's carbon dioxide. And so we're going to start with the graph on the left, and then I'll kind of orient you here. On the bottom axis is time, going from near present day on the right-hand side, back about 800,000 years on the left. On the left-hand axis, you see carbon dioxide concentrations in parts per million. And if you take a look, you can see that that CO2 concentration goes up and down in a very regular manner. And that's because of the way the Earth revolves on its axis and wobbles on its axis and revolves around the sun. And so those natural variations from about 200 parts per million to 250, sometimes close to 300, that's what explains the ice ages and the interglacial periods like we're in now. But if you take a look at the graph, near present day, there's this huge spike in CO2 concentration. And so if you look at the graph to the right, this just shows you from 1960 to near present day. And you can see we go from 320 to what you see in the green box at the bottom. The latest measurement from Mauna Loa in Hawaii is 423 parts per million. So 200 to 250 roughly is normal. 423 is where we are right now. So clearly something happened. For some reason, we got a whole bunch more CO2 in the atmosphere. Well, this graphic shows you the carbon cycle. And don't worry about any of the arrows or numbers. The big takeaway from here is that carbon occurs in 4 reservoirs on our planet. One is the oceans, one is the atmosphere, a third is the biosphere, which is all living things, including us, and the fourth is a geologic reservoir. Now, the geologic reservoir historically was sealed, if you will. The CO2 moved around between the other 3, but that geologic carbon was kind of stuck underground until we learned how to use fossil fuels, coal, oil, and natural gas. So we started burning those and then releasing that geologic carbon into the atmosphere and into the oceans. And so that's why we see that big spike in CO2. And in reality, most of the CO2 that we've generated by burning fossil fuels has actually gone into the oceans, which are also starting to heat up now and seeing a number of other effects as a result of this increased CO2 level. So that's why we're seeing this increase in temperatures and precipitation and other things I'm going to get to here in a minute. So now let's kind of take a global perspective. And at the graph on the left, you'll see what's called a global temperature anomaly chart. And this is from last year. And the way you interpret it is that reds and yellows are significantly warmer than historical averages, white is average, and blue is below average. And you can see that the planet is pretty much significantly warming everywhere, but really what jumps out at you is what's going on in the Arctic. You can see just how red it is up there. So now take a look at the graphic on the right. And this shows you the sea ice extent from September 18th of last year. So that was the sea ice minimum for last year. You'll see an orange line here. I'll kind of trace it with my cursor. That is what historically would be the extent of sea ice in September. But you can see that there's a whole lot of open water here. And that's important because of something called the albedo effect. So this graphic kind of demonstrates that. If you look at the bottom, when sunlight hits snow and ice, 90% of that energy just bounces back into space as light. Only 10% is converted to heat. But if you look at the little square at the top, you can see when sunlight hits open water, fully 94% of it is converted to heat. Only 6% bounces back out into space as light. So a little bit of water causes a lot of warming. It's a positive feedback loop. So you get a little bit of open water, warms rapidly, melts more ice, which then exposes more water. And so it's really significantly decreasing the ice cap. The other thing this graphic doesn't show is that the ice that remains is much thinner than it used to be. So you might think that this is kind of abstract and esoteric and, you know, we don't live in the Arctic, but I'm going to show you how this has direct implications on our weather and climate here. So now we're going to look at some temperature anomalies from a national level. So once again, these aren't projections. This is what's happened so far. So on the left-hand side, you will see annual temperature, both annualized across the whole year, and at the bottom broken down by seasons, winter and summer. This is from the 4th National Climate Assessment. So this data is probably 5 or 6 years old. There's going to be a new National Climate Assessment coming out this year. But you can see pretty much the entire country is significantly warmer than historical averages, especially during the winter. You will notice that there are some areas of blue on this map. I think that's going to go away when the next National Climate Assessment comes out. So that's why I have this other map here, which is from a different source, but shows you that the entire country is significantly warming compared to normal historical averages. So where are we going to go? Well, so far, we've seen a 1.8 degree Fahrenheit increase in temperatures. And we're seeing significant impacts as a result of that. And I'll talk about that in a minute. But if you look at these graphics here, we'll start at the top. This is from a climate impacts assessment for Pennsylvania. And the top shows you the average annual temperature. The kind of historic is in the upper left. And if you take a look, by the end of the century, and this is what we call worst case scenario. That's if we don't get our emissions under control rapidly. So this is the path we're on now. You'll see that by the end of the century, we are going to see probably anywhere from a 3 to 4 to maybe 5 times greater temperature increase than we've seen already. If you look at the graphics below that, this shows you the number of days with temperatures above 90 degrees. And so the map on the left shows you the kind of the observed historic. Most of the state doesn't see a whole lot of plus 90 degree days. The Philly area tends to see more. But by the end of the century, many parts of the state are going to see perhaps 3 months or more out of the year with greater than 90 degree temperatures. So it's kind of hard to wrap your head around exactly, you know, so it's 1.8 degrees. How do I relate to that? Well, there is a website called 1001 Blistering Future Summers. And you can go there and plug in the city or town where you live or the closest one. And it will show you the average temperature during the summer today and what it will be like at the end of the century. So I put in State College, the center part of the state, and you can see the average summer temperature currently is 80 degrees. By the end of the century, that will be above 91 degrees. So it will feel like Kissimmee, Florida. And you may have been to Kissimmee or Orlando nearby where Disney World is and say, hey, I like it down there. But if you think about the kinds of plants and animals that live in Central Florida, if you think about the kind of crops they grow there, it's totally different than we have here now. If this were to actually happen, the analysis shows that the necessary habitat for most native species in Pennsylvania will not exist here at the end of the century. So this really would be catastrophic. So we've been talking about warmer temperatures, and one thing that comes along with warmer air temperatures is that warmer air can hold more water vapor. And more water vapor in the air the more rain that's going to come out. So you have probably noticed changes in rainfall patterns. Most people have. Overall, we've seen a 10% increase in annual rainfall, but that's not the real story. The real story is how the rain is coming. It's coming in these really heavy rain events. And so the map you see there shows you the percent increase in what they define as very heavy rain events, those that would normally only occur 1% of the time. And so you can see the Northeast has a 55% increase in those heavy rain events. And if you drill down to Pennsylvania, we've seen more than a 70% increase in those heavy rain events. And it manifests itself in a couple of different ways. So the photo at the lower right is from our Loyalsock State Forest. And there was a road and a bridge there, and you can see there's a culvert, a traditional culvert that's a pipe. We've had 3 500-year rain events in a 3-year period in the Loyalsock State Forest. So that's really kind of unprecedented and unheard of. The photo above that is from what'll be, I guess, 3 summers ago now. And this is Interstate 283 between Harrisburg and Lancaster. It was a Friday afternoon. People were driving home from work and a thunderstorm developed, and it dumped more than 6 inches of rain in a very short period of time. That flooded roadway is nowhere a stream or a floodplain or a culvert. It was just so much rain fell that it literally filled up the road and people got stuck. And so we're seeing more and more of these really significant heavy rain events. PEMA, who oversees a lot of emergency management, likes to say now that if it can rain, it can flood. You can live at the top of a mountain now, and if you get one of these heavy thunderstorms develop, you can get flooding at the top of the mountain because the ground simply can't absorb it. So let's jump back to the Arctic, because we're going to relate what's happening in the Arctic to things like that thunderstorm. So the graphic on the left shows you the jet stream. So the jet stream is that river of air that moves our weather patterns across the country. Under normal circumstances, it's like on the globe you see at the left, it's very linear and it moves pretty fast. That jet stream is there because of the temperature differential between the Arctic and the equator. But we've already talked about how much warmer the Arctic is becoming. As a result, the temperature differential is much smaller than it used to be. And so what happens is you get the jet stream starts to slow down and it gets really wavy and wobbly. And so that means as storms develop or as weather patterns develop, they don't move, they just sit, like that thunderstorm that Friday afternoon near Lancaster. It also leads to big pockets of warm air moving very far north into the Arctic, so that we have situations like happened the summer before last, where well inside the Arctic, in Siberia, the temperatures went above 100 degrees. It's also leading to massive wildfires, both in the forested areas, but also even in the permafrost. So if you look at the winter kind of counterpart to this, the vortex, it's the same thing. It's driven by that temperature differential. So normally the polar vortex is this ring of wind that goes around the northern part of the planet, and it holds the coldest air way up north. But now, because of that shrinking temperature differential, you see that it's getting wavy, and we get those pockets of cold air going north and warm air going north and cold air coming south. And so it's not unusual now for several days each winter for the temperatures in Florida to be colder than they are in many parts of Alaska because of this wavy polar vortex. So it's kind of counterintuitive, but there's one well-known climate scientist who likes to refer to climate change as global weirding, because a lot of the impacts aren't what you would expect. All right, let's talk about snow, because this is another thing a lot of people are really beginning to recognize. We're getting a lot less snow than we used to. So the graphic on the left shows you a bunch of circles, orange and blue. The orange circles are places where they're getting more rain and less snow during the winter time. And you can see it's pretty much everywhere. The graphic on the right is from our Pennsylvania Climate Impacts Assessment. And so the map on your left shows you the number of days per year where snowfall could occur. This is kind of the historic record. So in the northern part of the state, where I think most of you folks are from, you're looking at 70 to maybe 80 days out of the year, potentially where it could snow. By the end of the century, you see that drops to 30 to 40 days. Some parts of the state are 10 to 20 days. So we're already seeing less snow, and that's going to significantly increase. But once again, there's exceptions to every rule. And so let's talk about lake effect snow. The photos you see on the right are from my hometown of Erie. This was from a couple winters ago where they had almost 200 inches of snow. They had 77 of those inches in just a couple of days, which then quickly melted. So it was a very strange situation. Well, the reason they got so much snow, you can see in the map at the upper right. This is the map of those days, and it shows you ice cover on the Great Lakes, and you can see Lake Erie is completely open. So you get those winds blowing over the lake, picks up that moisture, and then it dumps it in the form of snow downwind. Now, the graphic you see at the lower right is a radar image from one of those lake effect snow events. And what I want to point out here is that you can see there's a lake effect snow band that reaches almost all the way to Harrisburg. It's not unusual for us to get lake effect snow bands here. And actually, the winter before last, there was one storm event where the lake effect snow bands reached all the way from Lake Erie to the Chesapeake Bay. So we're seeing all kinds of really interesting and unusual events. So overall, a lot less snow, but sometimes you get a whole lot of snow in a short period because of this lake effect. Now, we're also seeing changes in our growing season. Here in the Northeast US, the growing season has increased by about 10 days, almost double that out west, which is a good thing, or it could be a bad thing. If you're a farmer or a gardener like myself, that gives you more time to grow stuff. But what we're seeing a lot of now is what you see in the photo at the right. In the middle of that photo, you see a bunch of what look like dead trees. This is from one of our state forests. That's frost damage. So what happens is you get a really warm day and the trees start to bud, and then you get a freeze or a frost and it kills the bud. Eventually the tree will rebud and it will grow leaves. So it doesn't kill the tree, but what it does is it prevents that tree from producing any fruits or nuts or seeds. So that has implications for wildlife. And also, until those leaves reemerge, a lot more sunlight reaches the forest floor and it starts to dry it out. So it changes the hydrology of the forest as well. Now, imagine everybody on the call today is really familiar with what invasive species and pests are. Unfortunately, almost all invasive species do better under a climate change scenario. And I have just two examples here. On the left is kudzu, which is known as the vine that ate the South. It was imported from Asia for cattle feed, but nobody bothered to ask cattle if they liked it, and they didn't. So it escaped. In many parts of the South, you see kudzu growing everywhere. It covers trees and it pulls them down. It covers buildings. But these photos I took in the city of Lebanon a couple of years ago. So you can see it's growing, it's flowering, it's making seeds, and the birds like the seeds, and you know what happens then. So we're seeing an increase in kudzu in Pennsylvania. But of much more concern is what you see on the right, and that's the hemlock woolly adelgid, which is an invasive pest that kills our state tree, the hemlock. Historically, the adelgid was held to the southern part of the state because it doesn't like really cold winter temperatures. But as winters have warmed, the adelgid has moved across the state and is pretty much found, I think, in almost every county in Pennsylvania now. So it is decimating our native tree, the hemlock, which is a bad thing, but it's not just bad for the tree, it's bad because it's those hemlocks that shade and cool our cold water streams, which is home to our state fish, the brook trout. So what we have here, this is from the EPA, are projections in changes in fish habitat in Pennsylvania. And so the area on the left-hand side is the worst case scenario, which is the path we're on. The right-hand side is the best case scenario if we really quickly get our emissions under control. You can see in the worst case scenario, all our cold water fisheries are going to convert to warm water fisheries. So there'll be very little brook trout habitat left. On the right-hand side, even under that best case scenario, you can see we lose a huge chunk of our cold water fisheries because they convert to warm water fisheries. but will retain some pieces in the Poconos and in the Laurel Highlands. So let's switch gears a little bit and talk about some health implications of climate change. And we'll talk about Lyme disease first. I'm sure everybody on the call has heard of it. Many of you have probably had it. I've had it twice myself. It's the #1 leading workman's compensation claim for the department I work for. And the reason is that the warm weather has allowed ticks to be active year-round, and they are reproducing more rapidly, and that is leading to the spread of the spirochete, the Lyme spirochete that they carry. If you look at the maps on the left, you can see just how fast it started to spread. The map on the right shows you Pennsylvania is really dark in there. It's because 1 out of every 3 Lyme disease cases in the nation are in Pennsylvania. We're kind of ground zero for Lyme disease. This is just one of the tick-borne diseases. There's a number of others that are even nastier, but we won't have time to get into those today. But ticks aren't the only vector that we're concerned about. We're also concerned about mosquito-borne diseases. And there are 2 reasons why we're seeing an increase as a result of climate change. One is because mosquito season is longer than it used to be, and the other is because we're getting an invasive mosquito moving in. So let's start with the length of mosquito season first. At the upper left-hand side, you'll see a graphic there that says disease danger days. You can go to this website, put in the city or town where you live, and it will show you how much longer the mosquito season is now versus 1970. So I have Erie up here because that's seen the greatest increase in Pennsylvania. And you can see that since 1970, mosquito season is almost a full month longer than it used to be. On the right-hand side, you see a photo of the Asian tiger mosquito. This is an invasive mosquito from Asia that is now found in the southern tier of Pennsylvania and even in the northwest part of the state. So it's found in Erie, for example. It's very easy to identify by those stripes and also by the way it feeds. It's active during the day. Unlike most mosquitoes at night, it's active during the day and they bite really hard and really fast. You'll know if you've been bitten by one. And they carry their vector for a lot of different diseases, things like Zika and dengue and chikungunya. Those diseases aren't in Pennsylvania yet, but we have the vector, so that's kind of the first step. It also carries West Nile virus, as do our native mosquitoes. And the reason I have the photo of the ruffed grouse here, which is our state bird, is that ruffed grouse populations have crashed. And a big part of that is because they're very, very susceptible to West Nile virus. So at the increased mosquito season and the increased mosquito populations, that's really put our state bird at risk as well. All right, so let's talk a little bit how our species is going to respond to climate change. And there's really 3 things that will happen. One is you're going to adapt to climate change. So think of things like white-tailed deer that are very adaptable. They're going to be fine. I also have a photo there of a timber rattlesnake, a real cool critter. We've done a climate vulnerability analysis for about 150 Pennsylvania species. And a timber rattlesnake is one that looks like it will probably do better under a climate change scenario. But if you can't adapt, then your next option is you're going to move. So if you think of things like birds, they're pretty mobile, so they have that advantage. Unfortunately, most of the research that's been done so far is showing that many bird species aren't going to do well because they have to have a place to go that has the right habitat, and the timing of natural cycles have to be appropriate so that when those birds reach their new destination, particularly insects have to be available to feed their young. And right now, there's a mismatch there because things are moving and evolving at different rates. And then if you can't adapt and you can't move, then you're probably going to die out. And so generally speaking, amphibians are in a bad way. And I have 2 examples here. On the left is our state amphibian, the hellbender. On the right is the spadefoot toad, which is about the size of your thumbnail. Has a very specific habitat requirement, spends most of its life underground. And as you can imagine, these guys have a tough time, picking up and marching 100 or 200 miles farther to the north. In terms of the most at-risk group of animals from climate change in Pennsylvania, it's freshwater mussels. So those are your three options. So the question is this happening yet? And the answer, it is. The Audubon Society has done an analysis of how much farther north all North American bird species are found during the winter. And almost all of them have been shifting their range, their winter range to the north. And some of them are pretty significant. The turkey is now 400 miles farther to the north. The robin has shifted 200 miles farther to the north. And then we have changes in migration. And so you see a picture here of a red-tailed hawk, which is our most common raptor in Pennsylvania. They used to migrate out of Pennsylvania during the wintertime, and for the most part, they don't anymore. They stick around because there's less snow cover and there's ample food supply. And then we have examples, and this is a really cool one, of a species that's moving north, eventually leaving the state, and a southern species coming in behind it. And so this is the black-capped chickadee and the Carolina chickadee. They look really similar. They sound pretty similar. They kind of fill the same ecological niche. And if you take a look at the map on the right, you can see the Carolinas here in the bottom in the orange, the black caps are in the gray, and there's a yellow line here. And this is a zone of hybridization because these two will hybridize. And that zone of hybridization is moving 1 kilometer per year to the north. So researchers are tracking this. And so you're seeing actual changes. The chicks you see here are hybrids. I photographed those at Hawk Mountain 6 or 7 years ago. And now I believe the Hawk Mountain area is completely switched over to Carolina chickadees. And so the question becomes, is this good or is this bad? It's probably neither. It's just an indication of what's happening. Now, it's not just animals that move, plants do too. And so here's one example, Virginia pine. So on the left-hand side, you will see the current distribution of Virginia pine. You can see there's not a whole lot of it in Pennsylvania. But on the right, at the top is low emissions or best case scenario. Bottom is high emissions or worst case scenario. Either way, you can see Virginia pine is going to become a significant part of the forest community in Pennsylvania. So we're going to see really big changes in our forests across the state. All right, so that's the doom and gloom. Let's talk about solutions now. And so what can we do about this? There's really two strategies. You have to use them both. One is mitigation or reducing greenhouse gases. So that means we stop burning fossil fuels. So we stop adding them to the atmosphere, but you could also include in this category removing them from the atmosphere. And we'll talk about both. And then because of what's called climate inertia, the amount of carbon we've already added to the atmosphere, even if we went to zero emissions today, we would probably see warming to continue for at least another 30 to 50 years. And so no matter what we do in terms of stopping the burning of fossil fuels, we still have to adapt to what's coming. And so we're going to touch on both of these. So we have developed a climate adaptation plan at DCNR. It is available on our website. And I'm just going to talk about a couple of things here, and then we can go to questions. So once again, this is from a perspective of DCNR. So as you probably know, we're 124 state parks, over 2 million acres of state forest. And we're also the technical advisors to all the private forest landowners in Pennsylvania. So we really need to adapt to climate change for a bunch of reasons. But, you know, we had more than 42 million visitors in 2021. A lot of people use our state parks. And when you think of parks, you might not think of infrastructure, but take a look at the list there. And you can see we have a whole lot of infrastructure we have to worry about, including dams, and which is really important when you talk about these heavy flows. So let me just give you a couple examples of some of the things we're doing with infrastructure. The photo at the top, you saw already. That is the flooding that occurred in Loyalsock State Forest. So once again, that's a traditional culvert. It's a pipe. And so over time, even under good conditions, as the water flows through that pipe, it erodes the downstream side. So kind of a hole forms, and that pipe perches above the stream channel. And so it kind of disconnects the stream. The bottom photo is the type of culvert that we're using now. You can see it has a much bigger opening, so it can handle a lot heavier stream flows. But you see there is no pipe and there's no bottom. And that means that that stream is now contiguous. And so as that stream warms, and we have things like brook trout or hellbenders that need to move upstream to colder water, they can do that now. So this allows for habitat connectivity in an aquatic ecosystem. In terms of conservation, we're doing a number of things. So if you think of climate change, it's been happening since the planet started. And if you think of those ice ages as that glaciers kind of ebbed and flowed across the landscape, plants and animals moved behind them. That's a lot harder now because we're here. So we have cities and towns. We have energy infrastructure like the power line right away you see there. We have a very, very fragmented habitat so that all those things that now need to move to the north or higher elevations to escape climate change have a difficult time getting there. Which leads us to the map that you see at the top here that we developed along with the Western Pennsylvania Conservancy, and it identifies areas that are critical for habitat connectivity for the movement of species. And for the most part, these are riparian areas or stream channels and rivers and ridge tops. And so what we're doing now is we're using this map, and as you take a look at it, you can recognize that things like the Allegheny National Forest is there, our state parks, our state forests, our game lands, but there's still a whole lot of that area that's privately owned and not under any kind of conservation easement. So we give out a lot of money in grants. Last year, I think it was $90 million. So we're using this map to guide some of that funding so that when it comes to land acquisition or easements, we're looking at the importance of that area for habitat connectivity. And we're also spending a lot of time looking at what kind of trees we can plant that will be better adapted to future climate conditions. Because common trees now, some of them like sugar maple and red cherry, aren't doing very well. And so we know we need to start addressing that. Wildfire management, the map you see at the top right shows you that we're probably going to see a 60 to 80% increase in wildfires. So we're doing a lot more controlled burns, like you see at the bottom, to control fuel loads. This year was a bad wildfire year. One thing we've noticed is that there's still a wildfire season, but now wildfires can occur year round, much more than they used to. So far this year, I think we're, in terms of the number of fires, we are more than twice as many as we normally see this time of year, and more than 3 times the acreage burned than we see normally at this time of year. So let's talk about what's called forest carbon sequestration. I mentioned that one of the things you can do is you can pull carbon out of the atmosphere. And what better way to do that than with trees? If you look at all the emissions across the US from power plants, more than 40% of that is taken up by trees. So managing forests to sequester more carbon, planting more forests will go a long ways to helping to address climate change. It's not the only solution, but it has to be a part of the solution. Towards that end, I know you can't read this at all, but this is an example of work we've done with the US Forest Service and others to look at, by physiographic region, all the tree species we have and whether they're going to potentially do better, worse, or stay the same, or new species coming in. And so there is a QR code there. Actually, if anybody's interested, you can just drop me an email or perhaps contact Barb and I can share with her the link where you can get these. Okay, so I have only 3 slides left, so I'm almost done. Because this can be such a depressing subject, I'd like to finish up talking a little bit about what you can do as individuals. And so you can reduce your carbon footprint. Look at transportation. If you don't need to drive, that's great. But if you do, look at an electric vehicle or a hybrid. My wife and I both drive hybrids. We're saving a ton of money on gas now. I drive into downtown Harrisburg every day. I get 40 to 50 miles to gallon. That's great. You can look at the energy use in your home. I have a picture of, LED lights. It seems like a cliche, but if you haven't switched them out, do it, and you'll be amazed how much money you're going to save. And you obviously reduce your energy use. And then here in Pennsylvania, we have what's called energy choice. You can choose where your electrons come from. And so I, for years, have been purchasing all mine from wind generated. I used to pay about 10% more than the average person, not a whole lot. Now I'm paying less because the price of renewable energy has fallen so much. Looking at your diet can be a really significant thing you can do for climate change. And so, Being a vegetarian would be great. If not, you can be what's called a flexitarian, where you perhaps reduce some of your meat consumption and you eat more locally produced foods. So I have that silly little graphic there of cows, and that's methane coming out of those cows, both front end and back end. They are really a very significant source of greenhouse gas because methane is 60 to 80 times more potent a greenhouse gas than carbon dioxide. There are places in the world where cows and the other ruminants are the #1 source of greenhouse gas emissions. New Zealand is an example. That's their #1 source of greenhouse gas emissions. And then in terms of eating locally sourced foods, they're healthier generally, they taste better. But I like to use strawberries as an example because when I was a kid, we only got strawberries a few weeks out of the year. It's when it was strawberry season. But now you can buy them year round in the grocery store. But think about where those strawberries came from. They came from South America. They were grown with fertilizer that came from fossil fuels, put in a plastic container made from fossil fuels, and it shipped under refrigeration thousands of miles. You can imagine the carbon footprint of those strawberries. And then finally, I always tell folks, if this is important to you, then think about it when you vote. And with that, I will take questions and stop sharing my screen.